aerodynamics today. Okay, so to start off, the first supersonic flight was achieved by Chuck Yeager in the Bell X-1. And there have only been two supersonic commercial airliners in production, the Tupolev Tu-144 and the Concorde. And in high-speed aerodynamics, the compressibility of air cannot be ignored, like in low-speed aerodynamics, which is around 300 miles per hour when the compressibility effects of air have to be factored in. The speed of sound is a good measure of flight regimes in a high-speed aerodynamics, which is based around Mach numbers, which is the ratio of the speed of the object compared to the speed of sound. And Mach flow regimes include transonic, supersonic, and hypersonic, and subsonic, but I won't be talking about that today. And each have their respective Mach numbers. So in transonic flight, which is approaching Mach 1, the speed of sound, most planes you'll see nowadays travel in this flight regime, like the Boeing 747, which has turbofan engines and swept wings. At supersonic speeds between Mach 1 and 3, you can see we have afterburner engines and swept wings as well, and the F-14 Tomcat. Now, at high supersonic speeds, between Mach 3 and Mach 5, afterburner engines are also used, and there's being research done into using ramjet engines. Now, these planes usually have very small wings to reduce drag, and in hypersonic flight, there's only been like one successful plane, the X-15, which is a rocket plane. It had a nickel alloy skin to resist heat. Now, supersonic airfoils are very different from conventional airfoils. They usually come in two different configurations, with the double wedge shape and the biconvex shape. The supersonic airfoil designs have a sharp leading edge because at high speeds, a blunt edge, like in conventional airfoils, causes a bow shock from the compression of air, while a sharp leading edge creates oblique shock waves. Now, airfoil designs at supersonic speed use oblique shock waves and expansion fans to create lift. Oblique shock waves are areas of high pressure around the leading and trailing edge of the airfoil, and they have slower moving air, which occurs when the airflow turns on itself and compresses at high speeds. And the opposite of these are expansion fans, which are areas of low pressure and faster moving air around the convex corners of the airfoil right here. Now, normally in supersonic flight, these oblique shock waves and the expansion fans, when the angle of attack is 0, these forces of pressure balance out, creating no lift. However, with an increase of the angle of attack, the strength of the oblique shock wave leading off the bottom of the leading edge and the expansion fan off the top of the concave curve of the airfoil generate lift on the plane. Wave drag is a form of drag created by the energy required to form shock waves, and this is the general idea of the sound barrier, which is a sharp increase in drag according to Mach number around Mach 1, which cannot be broken before 1947 with the X-15 Chuck Yeager. Okay, now most supersonic and transonic planes have swept wings, and swept wings are a design choice to slow down the airflow over the wing to subsonic speeds. Now this reduces wave drag from the compression of the air using shock waves, and this allows for supersonic airfoil and subsonic airfoils on supersonic aircraft, like the X-14 Tomcat. Now in conclusion, the different flight regimes are based around the different Mach numbers of flight, and in supersonic flight, compressibility of air must be taken into account because of the new mechanics of lift using oblique shock waves and expansion fans, and also the new form of drag, wave drag, from creating the oblique shock waves. Okay, moving right along, we have our mathematician and a scientist, Gauss and Joukowski. Mathematician Carl Friedrich Gauss was born in 1777 and died in 1855. He was a German mathematician and has been called the greatest mathematician since antiquity. His contributions to math include the Discretiones Arithmeticae, the construction of a regular heptadecagon, the proof of the law of quadratic reciprocity, and the prime number theorem. The book Discretiones Arithmeticae was written when Gauss was 21 and published in 1801. Now this book is important because it was the first comprehensive book dedicated to the study of number theory, and it was a collection of Gauss's own proofs and others. Gauss is also notable for constructing the regular heptadecagon in 1796 using the compass and straight edge, which required the calculation of the cosine of 2 pi over 17. And the law of quadratic reciprocity was first stated by Euler, but Gauss was the first person to generate a valid proof of this theory. And it involves a modulo function that, in the prime number theorem, Gauss says it's the asymptotic distribution of prime numbers to figure out how many prime numbers there are as numbers become larger. And this function is the number of primes less than n, which decreases, and which increases as the numbers become larger. Now, Nikolai Joukowski was born in 1847 and died in 1921, was a Russian scientist and considered a founding father of both aero and hyperdynamics. His contributions include the Joukowski transform and the Kutay-Joukowski theorem. For the Joukowski transform, it's a calculation of the two-dimensional potential flow around the airfoil and the speed of the flow across the airfoil using this equation derived from the circle. And from the Kutay-Joukowski theorem, this is a theorem to calculate lift on the rotating cylinder related to the speed of the cylinder, the density, and the circulation, which is the angular velocity. And this is a lift. The equation for this is the lift per unit length equals rho GV, where G is 2 rho times the angular velocity and the radius of the cylinder squared. Thank you.